Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand intellectual theatre of 20th century physics, few problems have commanded the stage with such persistent and enigmatic authority as the nature of turbulence. For generations, the chaotic walls and eddies of a fluid in motion represented a final frontier of classical mechanics, a domain where the elegant predictability of Isaac Newton's laws seemed to dissolve into an intractable statistical morass. By the mid-century, a consensus, elegant in its conception, had formed around the picture painted by the Soviet physicist Lev Landau and independently by Eberhard Hopf. This prevailing view held that the transition from smooth, laminar flow to full-blown turbulence was a gradual accumulation of complexity. The physical system, as it absorbed more energy, would undergo a sequence of instabilities, each one introducing a new, independent frequency of oscillation into the flow. Mathematically, this corresponded to a series of what are known as Hopf bifurcations, with the system's trajectory in its abstract phase space evolving from a stable point to a simple loop, then onto the surface of a two-dimensional torus, a three-dimensional torus, and so on, ad infinitum. The resulting motion was quasi-periodic, a superposition of a vast, ever-growing number of incommensurate frequencies. Turbulent flow, in this Landau-Hopf framework, was essentially an infinitely complicated symphony of regular oscillations, its state residing on a geometric object of very high, or perhaps infinite, dimension. It was a theory of profound intuitive appeal, suggesting that immense complexity arose from an immense number of contributing simple parts. Yet, it harboured a subtle, fatal flaw. When experimentalists measured the frequency spectrum of a turbulent fluid, they found a continuous, broadband distribution of power, a noisy roar. The Landau-Hopf theory, with its discrete, albeit numerous, frequencies, predicted a spectrum composed of a dense forest of sharp, distinct spikes. The theory and the physical reality were in clear discordance. It was into this charged intellectual atmosphere that David Buell, a Belgian mathematical physicist, and Floris Takens, a Dutch mathematician, released their 1971 paper on the nature of turbulence. This work, a compact and mathematically dense piece published in Communications in Mathematical Physics, amounted to more than a mere critique. It was a conceptual revolution, one that proposed a radically new geometry for the onset of chaos and, in doing so, laid a cornerstone for an entirely new field of science. The Ruelle Takens paper advanced a startling and profoundly counterintuitive thesis. The immense complexity of turbulent behaviour required a surprisingly small number of active degrees of freedom. The intricate, aperiodic motion observed in fluids could emerge from deterministic systems governed by a few coupled, nonlinear equations. They argued that the serene, high-dimensional torus envisioned by Landau and Hopf was an unstable and fragile mathematical construct, drawing upon the deep and abstract developments in dynamical systems theory, particularly the work of the mathematician Stephen Smale on hyperbolic systems. Ruelle and Takens demonstrated that the path to chaos was far shorter and more abrupt than anyone had previously imagined. Their central mathematical result was a theorem of devastating elegance. They showed that in a system whose state evolves on a four-dimensional torus, representing a quasi-periodic motion with four independent frequencies, a generic, infinitesimally small perturbation would be sufficient to destroy this regular structure. The stable, predictable motion would collapse, replaced by a trajectory confined to a much more complex and bizarre subset of the phase space. They later conjectured, correctly, that this instability could manifest even with three frequencies. On a three-dimensional torus, the system, after a mere handful of bifurcations, would cease to be quasi-periodic and would instead become truly chaotic. The fluid dynamics community, accustomed to the gritty realities of wind tunnels and the formidable challenge of the Navier-Stokes equations, greeted this intrusion of abstract topology with a certain degree of well-mannered bewilderment. The object at Ruelle and Takens proposed to replace Landau's infinite-dimensional torus was something they termed a strange attractor. The name itself, a poetic and evocative label for a rigorous mathematical concept, captured the dual nature of its behaviour. It is an attractor because, like a stable point or a simple limit cycle, it is a region in the phase space towards which all nearby trajectories of the system eventually evolve and become trapped. Once a system's state enters the basin of this attractor, it remains on the attractor forever. The strange quality, however, is what constituted the revolutionary insight. A strange attractor possesses a fractal structure it has detailed all scales of magnification, an infinite intricacy packed into a finite volume of phase space. A cross-section would reveal a pattern of points resembling a Cantor set, a geometric object with zero volume, yet an uncountably infinite number of points. Motion on this attractor is aperiodic, meaning it never repeats itself. Most critically, it exhibits what is now famously known as sensitive dependence on initial conditions. 2 points on the attractor, starting arbitrarily close to one another, will diverge from each other at an exponential rate, their future trajectories bearing no resemblance after a short time. This exponential separation, quantified by a positive Lie upon of exponent, makes long-term prediction impossible, though the system remains entirely deterministic. Randomness, the paper suggested, was an emergent property of simple, non-linear deterministic rules. This new paradigm resolved the great paradox of the turbulent spectrum. A quasi-periodic motion on a Landau-Hopf torus, being a sum of discrete frequencies, produces a line spectrum. The chaotic, aperiodic wandering of a system on a strange attractor, however, contains a continuous range of frequencies. The trajectory's constant stretching and folding within the attractor's fractal geometry inherently generates a broadband power spectrum, the very signature that experimentalists had consistently observed in turbulent fluids. The Ruelle Takens model, born from abstract considerations of generic properties in dynamical systems, provided a perfect qualitative match for the physical data, where the previous theory had failed. It was a stunning confluence of pure mathematics and observational physics. The paper accomplished a monumental synthesis, translating avant-garde concepts of Smale's structural stability program into a concrete physical hypothesis. It posited that the onset of turbulence was a low-dimensional dynamical phenomenon, a behavior that should be observable in carefully controlled experiments long before the full, spatially extended complexity of high Reynolds number flow took hold. The paper was a direct challenge to experimentalists' search for the fingerprints of low-dimensional chaos and transition to turbulence. The scientific community's response was initially cautious. The argument was mathematically sophisticated, and its conclusion that the magnificent complexity of a waterfall could be rooted in a system with the effective dimensionality of 3 or 4 strained credulity. A theory appeared to be a statement about generic systems of differential equations, and its direct, rigorous connection to the specific and notoriously difficult Navier-Stokes equations governing fluid motion remained an open question. For a time, the Ruelle Takens picture and the Landau-Hopf picture coexisted as competing hypotheses. The decisive verdict would come from the laboratory. In the late 1970s, a series of landmark experiments, most notably those conducted by Jerry Golub and Harry Sweeney at the City College of New York and the University of Texas at Austin, provided the crucial evidence. They studied a system, known as Coët-Taylor flow, where a fluid is confined between 2 concentric rotating cylinders. By carefully increasing the rotation speed of the inner cylinder, they could observe the fluid transition from smooth, laminar flow through a series of increasingly complex states. Using laser Doppler velocimetry to make precise, local measurements of the fluid velocity, they analyzed the resulting time series data. They found that after only 2 distinct oscillatory modes appeared corresponding to motion on a 2-dimensional torus, the sharp spectral peaks would suddenly broaden, giving way to a continuous spectrum. This was the signature of chaos. The experiment provided powerful confirmation that the route to turbulence, at least in this system, followed the path predicted by Ruelle and Takens, with chaos appearing after a very small number of bifurcations. This experimental vindication was powerfully enabled by a subsequent theoretical contribution from Floris Takens himself. In a 1981 paper, he proved a remarkable embedding theorem that provided a practical recipe for experimentalists to reconstruct the geometry of an attractor from a limited set of data. Takens' theorem showed that by measuring a single scalar variable over time, say the velocity at one point in the fluid, one could reconstruct a faithful topological picture of the entire system's attractor in a higher dimensional phase space. This technique, known as phase space reconstruction using delay coordinates, became an essential tool in the arsenal of the nonlinear dynamicist. It allowed researchers across numerous disciplines to take a single time series, be it from an electrocardiogram, a fluctuating animal population, or the stock market, and search for the underlying geometric structure of a potential strange attractor. This made the abstract ideas of the 1971 paper empirically testable and widely applicable. The work of Ruelle and Takens, therefore, did more than propose a new theory of turbulence. It provided the conceptual and practical foundations for an entirely new way of analyzing complex data. The legacy on the nature of turbulence extends far beyond the confines of fluid dynamics. It is rightfully considered one of the founding documents of chaos theory, a scientific revolution that reshaped our understanding of complexity and predictability in the latter half of the 20th century. The paper's central idea, that simple deterministic systems can generate apparently random behavior, has permeated nearly every corner of science. The concept of the strange attractor, first proposed as an explanation for turbulence, was quickly recognized as a universal feature of nonlinear systems. It provided a framework for understanding phenomena as diverse as the irregular pulsations of variable stars, the unpredictable weather patterns studied by Edward Lawrence, whose work ran parallel to their own discoveries, the dynamics of chemical reactions, the firing of neurons, and the fluctuations of ecological systems. The paper, along with Lawrence's seminal 1963 study and the later work on universality by Mitchell Feigenbaum, formed the intellectual trinity upon which the new science was built. It gave scientists a new language and a new set of tools to describe the irregular, aperiodic phenomena that are ubiquitous in nature, phenomena that had previously been relegated to the category of incomprehensible noise. The very word chaos, endowed with its specific technical meaning by the mathematician James York, entered the scientific lexicon as a direct consequence of this emerging paradigm. In retrospect, the 1971 paper by David Ruelle and Floris Takens stands as a testament to the power of interdisciplinary thought and mathematical abstraction in confronting the most challenging problems of the physical world. It was a bold and audacious work, one that dared to replace an established and intuitive physical picture with a radical, mathematically grounded alternative. It looked at the seemingly infinite complexity of a turbulent cascade and saw the ghostly outline of a low-dimensional, fractal object. The paper's success lay in its ability to connect the highest levels of pure mathematics with concrete, measurable physical predictions. It shifted the focus of research from a purely statistical description of fully developed turbulence to a geometric and dynamical understanding of its onset. While the problem of fully developed turbulence remains one of the great unsolved challenges in physics, the Ruelle Takens theory fundamentally altered the nature of the inquiry. It demonstrated that within the heart of deterministic laws lies a capacity for creativity and surprise, an ability to generate infinite complexity from finite rules. The strange attractor is more than a mathematical curiosity, it is a profound metaphor for the intricate and often unpredictable beauty of the natural world, a world where order and chaos are two sides of the same deterministic coin. The quiet, technical paper of 1971 did more than just explain the nature of turbulence. It forever changed our understanding of the nature of nature itself.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.